Alright, now we're on to outliers. So this is the third video of my data screening in R set, and we're going to cover how to screen for univariate and multivariate outliers. Right, bonk. Let's turn off the sound here first. So outliers can really be problematic because they bias parameter estimates, which were normally the mean, maybe regression coefficients, those sorts of things. And so if you look at the mean here with no outlier, that's a better representation of all of these scores up here than the lowered mean with the outlier. So the mean is heavily biased by the outliers in the data. So it is a big problem that you have if you have a lot of outliers. So what the outliers also heavily bias the variance estimates, the standard deviation and standard error. And so if you look at the differences with the outlier and without the outlier, the estimate, the error of that estimate, it gets bigger. And so you have a wider standard deviation. And so you want to make sure that you at least check for outliers so you know if they're a problem with your data. So what is an outlier? It's a case with an extreme value on one or more variables. And why might they occur? Well, you might have put the data in wrong, but at this point you've already checked for accuracy, so hopefully that's not the issue. Maybe it's not the population of people you meant to sample, so it's a real case, but you didn't want to get those types of people. Or you might have a truly skewed distribution. So it is from the population, but that population has a really long tail and has some very extreme values, and you got those. The other issue is that sometimes you can find data that's been entered by participants who don't care. So if they're taking a survey, they might click 1 the entire time or 7 the entire time. They might make patterns with the data, like 1, 2, 3, 4, 5, 6, 7, 7, 3, 5, 4, So they've just clicked the buttons so it looked pretty to them rather than taking the survey. Those people are also outliers. Well, they're outliers because they're not the population you meant to sample, right? Those are not the people's actual scores. That's just a hot mess. So screening for outliers can also find those sorts of problems. There are other ways to screen for that type of data. Careless responses is what they're called. So there's two basic types of outliers. Univariate outliers for univariate stats when you have one dv or one y variable. Multivariate outlier for when you're dealing with multiple variables that you want to check on. So with univariate outliers, what you can do is use this scale function in R to z-score your data. So back to my little outline I've been kind of hacking together here. So we've got outliers, and now we're doing univariate outliers. You can use the scale function, okay? And that creates z-scores. Okay. And with z-scores, what you do is you look for people whose cutoff score is, sorry, this is one here. It's a typo I forgot to fix. These are people who are less than 1% of the population. So the big important rule, we want to screen people whose scores are 0.001 or worse. That's where the 1% comes from. And so a z-score of 3 is close enough to that 0.001 rule that we'd want to use that as our cutoff. The real score is 3.28, but 3 has been a rule that's stuck for a long time. So most people use a z-score of 3. And that's absolute value. So greater than positive 3 or less than negative 3. Those people's scores are very, very different. So that means they're 3 standard deviations away. They're less than 1% of the population. They're less than 0.1% of the population, excuse me. And so their scores are really wacky. And that's very far away from the normal part of your data set. So you want to exclude those people. Or you'd want to exclude that particular score. But let's say you have 300 columns. You would have to do that 300 times. And there are ways to automate this sort of thing in R, but what do you do if they have one bad score here, one bad score there, but otherwise they're fine? So it becomes kind of a tedious adventure. So they're fine and dandy. But let's say I want to do everyone at once. So what I'm going to teach you how to do here is how to look at Mahalanobis distance scores. And those scores will allow you to screen all the columns and all the people at once. And and it will calculate how odd their pattern of scores is. Instead of how odd is this one score given all these other scores, this is how odd is their pattern of data given all the other data. And I find that to be a better analysis. It also is a little quicker. So the multivariate outlier analysis that we're about to do works on 1 column or 500 columns. So you might as well do it the entire time. So we had to find some new way to measure distance because z-score is a distance from the mean. That's the point of z-scores. But now we have multiple columns, so we want to do the mean of means. So we're doing everything at once. So Mahalanobis distance, first it creates a centroid. Centroid is the mean of all the means, so basically the mean of all the columns. And then it measures how far away your data point is from that centroid. It's not necessarily a 3D picture. If you have 3 columns, it's 3D. If you have more columns than that, it's, XD. But it's a Euclidean distance measure. And so the way I was describing it to my students was if you're on the football field at a football stadium, since it's football season, whoop, whoop, and you're standing on the field, and if you are the mean of the means, the people who are on the field with you are a certain distance away, but people up in the stands are further away. So if you're at Kyle Field, which is Texas A&M, because I'm an Aggie, and you're in the third deck, you're very far away from the people on the field. And so if you think about Mahalanobis as measuring sort of through space, it tells you how far away a person's patterns of scores is from the average pattern of scores. It's the easiest way to explain it. And so it's measuring how far away you are from the people in the stands. And so it's a hypotenuse measure, but it allows us to get a distance. So people who are very far away are outliers. Okay? Because this is a distance measure, everything is positive. So that makes life a little easier because we only have to deal with positive scores. Okay? However, unlike z-scores, which have a rule of 3, there's no one and done rule from Mahalanobis. Instead, you have to calculate it. But we're going to talk about how to do that in R2. Okay. So we'll use a chi-square table. We'll talk more about why chi-square here in a second. So my chi-square table, I found this one online. And then we'd have to use a specific degree of freedom, but mainly we want to use this 001. So I want to calculate only with this 001, and so it's this column here, based on a specific degrees of freedom over here. Now the degrees of freedom has nothing to do with degrees of freedom for hypothesis testing, which is normally n-1. So my little note down here, which should be in like big bold letters, but it's not. Instead, the degrees of freedom is the number of variables you're using to create that Mahalanobis score. Sometimes that's called K, but it's the number of variables that are used to create that score. And then we're going to use 001. We're going to make R do this on the fly for us, but I'll show you how it matches the table here in a second. So what do I do with those people? I've figured out who the outliers are, and so this is really the not black and white part of it. On many of my assignments, I tell students to delete them, so we end up getting the same approximate numbers at the end just to make sure they're doing it correctly. But if we're talking about real research here, I'm sort of in they're really far out from here. We're talking about 0.1%. So this is like a really improbable set of scores. So delete them. But a lot of people argue, well, those outliers don't make a difference if the sample size is large enough. Okay, don't delete them. Or, no, these are real people and these are real scores that real people could score, and I checked them and there's no careless responding. Okay, don't delete them. If your sample size is very small, you might not be able to delete them because you just don't have enough power otherwise. So, whatever. I don't know that I'm actually advocating phishing here. It's kind of a joke. But you could try the analysis with and without the outliers and see what happens. And if you do that sort of thing, I always tell people we got to report it. So in the journal article, talk about we screened for outliers using Mahalanobis distance. We found 3 outliers. We tested it with and without. Nothing changed. So here's the analysis with, or here's the analysis without. I've done that in several papers, and people, I think if we can get people to report those sorts of things, we might not see the reproducibility problems that we're having in psychology anyway. It's kind of a big topic right now. But just being honest with what you did with your data is important. So a quick side note. And this actually, it's not super important that this slide is in this video so much as it is in the next video, but we're going to do some fake regression analyses here in a little bit using some of the variables we're about to create, and that's just a way to create the data screening. And so when you're doing data screening that's sort of totally separate from the analysis, you kind of have to fake it to get some of the diagnostic plots that you're interested in. And so I'm going to come back to this idea again in the next video. For a regression-based test, though, you don't have to fake it. It is a real regression, and you can get the diagnostic plot straight at LM, no big deal. And so the reason these slides are in here is because if we're talking about outliers for regression, there are extra rules. So we'll talk about leverage and influence, mostly measured with leverage values and Cook's values when we get to talking about real regression. So there's a slightly different procedure for outliers in regression. Many of the functions that you get to when you run analyses, like AOV for ANOVA or LM, have their own special set of diagnostic plots and their own special set of rules, but this guide is a global analysis. So you could use it on, you could take these procedures and apply them to a bunch of different tests. All right, so those side notes aside. One thing we need to do is take out the factor columns. So Mahalanoobis won't really calculate on a factor variable. So I am going to drop those columns. So first thing I'm going to do is figure out who those are. So I'm using my filled in none data set. So I have excluded people who I couldn't replace their rows. And that's the first two videos. So I'm going to use all the rows and columns. And let's see here. I want to do the names function for filled in none to see what order they're in. And so I want to drop these first two factor columns. So it's 1 and 2. And they're in a different order than when I started, if you've been watching these videos, because of the way I stripped them off. I did the mean replacement, the mice replacement, and then now I've added them back together. So I'm going to drop these first two columns, but let's just check, make sure this is doing what we expect it to do. And there. So my RS8 isn't in line anymore, and I could move it around, but I don't really care that much. So I have all of my columns lined up that are not factored. So we're going to use the Mahalanoobis function. It's part of base R. And so the rules are the dataset name, call means for column means, dataset name, RM equals true to get rid of any missing data. So if you decide to delete people pairwise and you've added those rows back in, you can use this data screening guide no matter if you have missing data or not. COV for covariance tables, dataset name, use pairwise complete ops. Oops, there's a little, there we go. Quote here missing. Okay. And this is the delete NA's pairwise function as part of COV. Okay, it's also part of core for correlations tables. So how that looks here, it's kind of messy, so let's type it out. Is we're going to do Mahalanoobis. Well, I'm going to save those as Mahal, so Mahalanoobis. Okay. It's part of the stats package, so dataset name filled in none. But specifically minus columns 1 and 2. And that is because I want to exclude my factor variables. And then we're going to do call means with a capital M, so one of those rare capitals, dataset name, comma within call means na.rm equals true. So moving on to the next piece, it's cov for covariance table, same dataset name, comma, use equals pairwise complete dot ops. Type it just like that. So let's run that. 1, 2, 3. So now you'll see I have a Mahalanoobis column. If I look at that column, it's just a bunch of numbers. Well, that's not super helpful to me. So what can I do to look at those numbers? So now we're on the multivariate, and we're using Mahalanoobis. So I saved them, now what? So we can get rid of people with the bad scores. But what is a bad score? And let's just take a summary real quick of those Mahalanobis. So I did a summary of Mahal. It's going to show me that I have 2 NAs. Why do I have 2 NAs? Well, anybody who has an NA, their scores don't get calculated because you have to have all the column points to be able to be calculated. So these are people who in my RS8 column, the column with too much missing information to fill in, still have NAs. But they got included because we just didn't replace that column. So it shows me a max score here. And then you could also do the table function in Mahal, but this is going to be really messy. So this is not a useful thing for us to do. Instead, we're going to do something else. But we got to calculate some numbers first. So what are the bad scores? Okay, and we talked about this just a minute ago. So let me show you how to make R do this for you, and then we'll pull up the table and prove to you that number is correct. So we're going to use the Q chi-square function for quantile of chi-square. And anytime you talk about quantiles, you're talking about the cumulative distribution function. And that's a little confusing to people at first. But essentially what it does is it will help you calculate a kind of cutoff score. So you find the p-value point you're looking for, and you say, what's the cutoff at that point? But since it's a quantile function, it runs from 0 on the left to 100% or 1 probability on the right. So if we want 0.001, we're really looking for the point at which it's, 0.001 is in the tail. So we've got to find 0.999. So it's always giving me 1 minus that number. Let me see if I can draw this a little better. This is kind of one of those hard things to explain. So what we're doing is we're creating chi-square here. You'll excuse my terrible chi-square table. And so if I've drawn chi-square and it's not a horrible drawing, I want to find where this is 0.001 out here and 0.999 over here. And so like I said, it starts at 0 and it runs up to 1, and it never gets to 1 because it doesn't asymptote, but potatoes. So I want 0.999 here and 0.001 here. And so the rule is 1 minus whatever p-value you're looking for. And so we're going to save that as cutoff. So it's the 1 minus their p-value, which we've set as the big important rule to 0.001, so 999. And then in-call. In-call tells me how many columns are in the data set. So I'm going to use the same data set I did a second ago. So this is super important here. Whatever data set you used here, continue to use that data set here. So Q chi-square. I need the p-values, so 0.999, comma, degrees of freedom. Okay. You could also do lower tail equals true, which would give us, lower tail equals false, but I just find it easier if I can remember that it's 0.999. And so I've used the data set here, and so that's going to count the number of columns if I do in-call data set. Okay. So real quick, let's just run this. So number of columns of that data set. So it tells me there are 17 columns. And so that's actually my degrees of freedom. So let's see if we can estimate this before we get R to do it for us. So if I have 17 columns, right, the cutoff score should be 40.79 because I'm going to use p equals 0.001. I'm going to use 17 columns for my degrees of freedom. So that's 40.79. Now I'm going to run this cutoff score. And I'm going to type cutoff down here, and it's 40.79. So that is, or I can look at it over here. That is calculating the cutoff score for you based on the number of columns in the data set. I like this in-column function because then I don't have to remember to count correctly every single time. Okay. All right, so now you can calculate how many are bad, and this is a little easier because it shows you what's going on. So I'm going to take my summary function here. I'm going to just say how many people are less than the cutoff. Okay, remembering that chi-square is positive, so all these numbers are greater than 0. This is a 0 line. And so you want to know how many people are over here are not outliers. How many people are greater? Those people are outliers. You could do it either way. But I'm going to do less than, for reasons here we'll get to in a second. And only one person has a a score that's greater than the cutoff score. So if you say how many people are less than the cutoff, the falses are your outliers. So I got one outlier, and the rest of them aren't. So let's get rid of those people. I'm going to say no out for outliers is my data set I'm working with, where Mahal is less than cutoff. So this is why the summary matches how you would exclude them. And that's why I did my summary this way, is because this will exclude outliers. So let me type that here. I got no outliers equals filled in none. That's the data set we're working with. Mahal less than cutoff, because I want to keep people, I want people's scores who are less than the Mahalanoobis, the bad scores, so less than, because they're less than the cutoff score, which means they're okay. And I want to get all columns back. So don't continue to do this, because then you'll actually lose your categorical columns you work so hard to keep. So this is just so that you can calculate the right cutoff score, but down here I want to keep all the columns. So leave this blank. That keeps all columns. Oops. It helps if you spell cutoff correctly. There we go. And so you'll notice now no outliers has one less person than my filled in none. So I dropped 12 people from the beginning because they have too much missing data. And now I've lost one person as an outlier. And I can see all that by looking at the fact that I have them saved as all different data sets. So my no outlier data set is what I would continue to work with in the next video, which is going to cover assumptions. So that is how you can exclude people who are multivariate outliers. And then if you want to test your analyses with and without outliers, you just test it with no outliers and filled in none and see if you get a difference. So moving on to assumptions in the next video.